Okay, so what I want to talk about today is loosely centering around, the transition of power systems from the multi-machine system that is fuel-based that we have today to integrating more renewable generation. And the twist that I'm kind of putting on this is that, the renewables, of course, they bring in kind of their own problems, as we will see in a moment. But really, we're also changing the interface technology in the sense that today everything is synchronous machine-based, and then we're bringing in a lot of power electronics into the mix, and that then begs the question of how to control and analyze these things. Before I jump into this, I have this little quiz here. So what do you think this is showing? So what could the axis here be? This is related to a power system.
50 or 60 hertz, and then the frequency.
Yeah, so this is frequency, this axis here, and this is time. Any guess what happened here? It's a historical event that happened in the European system.
I think that was another system out of that had more inertia.
Yeah. So this is when West Berlin was reconnected to the European grid. So before the reunification of Germany, West Berlin was islanded, and they were basically running the system off of I think one or two synchronous generators, and they were actually using batteries for frequency control. And that was the result, and you see the frequency is not very well controlled. And then here, this was when it was basically reconnected to the European grid, which had all these large-scale generators, nuclear power mostly, and then you see the frequency all of a sudden being very well behaved. So the reason I'm bringing this up is that what people are mostly afraid of these days is going back to this over here, which for various reasons is not what you want. Yeah, I tried. It's just, you see the pointer is not. Anyway, so as I will show in a moment, that's maybe not the main concern here, but when you hear from people about these so-called low-inertia systems, this is basically what people are worrying about, right? So you get very poorly behaved system frequency. And taking a step back, as I said, why do we want to go through this transition? So we want to get to a more sustainable system. Then certainly one advantage of renewable generation that people keep bringing up is that we will have a more decentralized system, which may be more robust against outages, right? Because you don't have a single point of failure anymore. Then the other aspect is that certainly over here we have fully controllable generation, right? It's up to us to decide how much fuel to burn. Whereas, the main concern with renewables, if you were to ask people on the street, is that, okay, it's intermittent. I don't control the sunlight. I don't control the wind. But as I was mentioning, under the hood, there is an even bigger change of the interface technology. So the steam turbines or hydro turbines that you would be using today, they interface through these synchronous generators here. And now we're moving everything over to being interconnected through these power electronics. And the dynamics, especially in a network sense, right? If you take a system level point of view of the multi-machine system, they're very well understood. And then once you move over here, it's very poorly understood. And that's big topic here that we're going to talk about. And one of the key points here is interoperability. So in the conventional system as it is today, because these synchronous machines, they all have very similar physics, interoperability kind of comes a bit for free in the sense that we at some point decided on one particular machine technology to interface all of these things, synchronous machines with an excitation winding. Then we standardized a few controls around this, and so these things are relatively easy to make work under interconnection, whereas over here now, every technology comes with its own controls. Those controls may be based on relatively fragile design principles, and then you get very complex dynamics as a result. And there is also an upshot over here in the sense that the machines, because it's mostly just machine physics that govern the dynamics of the system, it's very hard to control. Whereas over here, if you talk about the power electronics and renewable generation, we have very fast actuation capabilities. We can very flexibly design the controls. So the key question then becomes, how can we leverage these things here to get to a new kind of sustainable and reliable system? And let me just briefly go over this outline here. I first want to talk a bit about basically current work in the last maybe 5 to 10 years on this topic. Just to set the scene. Then I want to talk a bit about recent work in my group where we try to expand this a bit. And then I want to talk a bit more about problems that have not been tackled. So with that in mind, let me jump into this one here. So just about everything that is grid connected today is using this so-called grid following control paradigm here. And the idea is, you have your power converter somewhere in the middle here. You have something that you want to interface, be it, solar PV, a wind turbine, or like a battery energy storage system. And you're basically assuming that the grid is just an infinite bus. So whatever power you want to dump into the grid, you can do it. It's not going to change anything in the grid. Frequency, voltage, nothing is going to change. And then based on this assumption, you can actually control the power converter here to stabilize whatever is behind it. So let's say stabilize a wind turbine at the operating point where it generates maximum power, or do the same for PV, or for a battery, kind of take care of battery protection and fulfill some secondary objective. And that's a problem in the sense that you're completely neglecting kind of the system needs, right? You're kind of optimizing for performance of what you're interfacing, but you don't really take care of the system, of stabilizing the system at all. So these things, they're typically called grid following control. I want to put a bit of a twist on this here in the sense that it's following the AC grid, but it's actually forming the DC grid. So if you look at things like high voltage DC transmission, these things typically stabilize the DC voltage here, and then you have a DC grid behind it. So they're actually grid forming on the terminal that, from the viewpoint of an AC system, you wouldn't really care about. But the bottom line is, this is relatively fragile because you need someone else to stabilize your AC system over here. So that's the problem. The counterpart to this that you would typically find in literature is the so-called grid forming control. And this traces back to papers in like the 90s and then was rediscovered as its own research field, I would say maybe 4 or 5 years ago. And the idea here is completely opposite. Let me control the AC terminal of a power converter to do something nice for the system, and let me just assume that whatever is feeding the inverter can just keep up and produce whatever power I need, which is equally unrealistic unless you put a massive battery there. And as an example, here you see droop control. So all of these things, they're somehow synchronized through the physics of the power system. So you see the active power injection into the system here as a function of phase angle differences and line parameters. So basically using that as a feedback signal to kind of determine your frequency and synchronize all of these converters here, which are basically, you can think of them as harmonic oscillators that you somehow need to synchronize to the correct phase difference. And again, the control objectives here are now that you would want to synchronize all these converters and you want to basically give a stabilizing response to the system. But the problem is now you're not dealing really with the constraints or dynamics of whatever you're interfacing. So if you interface a wind turbine or a PV panel, there are limits to how much power you can generate here. There are limits to the response time of this source, and this is all just completely neglected. And that's obviously also a problem. This is commonly called grid forming control. Again, with a viewpoint to generalizations where we also have DC networks that I will go through in a moment. Let me call this AC grid forming, but DC grid following. So it assumes that someone else is keeping this DC voltage here stable, and I can do whatever I want on the AC side. Okay, so the first challenge I want to talk about here is that this AC grid following control can be very fragile. So there are real-world incidents here. This happened in California in 2017, I think, where we all of a sudden lost 1.2 gigawatts of solar PV generation. And if this were to happen again today, there's so much solar PV in that system at times that you would lose the equivalent of a nuclear power station. And this outage here was just purely due to poor control, poorly designed controls. There's also a more systematic reason for why these things go wrong. So there's works here. I don't want to go into too much detail. If you want to see this, you can look it up in this reference here. But at the end of the day, this grid following control is assuming that this voltage at this capacitor here, this AC voltage, is not impacted by the power injection from the converter at all. So, but now once the system is dominated actually by these converters here, that voltage becomes a function of your power in feed predominantly, and you just create a positive feedback loop because you're controlling the power here based off of that voltage, which, again, is feedback into the control to determine that power injection here. So there is a certain tipping point, where you have too many of these devices or their rating gets too high, things just go wrong, and this just becomes a positive feedback loop from a system level perspective. Okay, so now that I've been talking about these things, here are some state-of-the-art grid forming controls. So these are all the controls you would encounter now if you go into Google and say, okay, please show me grid forming controls. The most prevalent one is the so-called droop control here. And this is really just trying to mimic the steady state response of a synchronous machine. But again, as shown to the AC system, right, it's not actually doing anything to the generation behind it. And that's a critical problem we will see in a moment. Then there's more elaborate versions of this so-called synchronous machine emulation control. And it basically takes a measurement at the terminal, runs it through a simulation model of a synchronous machine, a relatively high order model now, not just the steady state response that you see over here, and then actuates the converter to just look like a large synchronous generator. And this, for various reasons, is extremely problematic. So the utility is they're very hung up on this and saying, oh, this is going to save us. But the matter of fact is that the power converter here has very different limits in terms of internal energy storage, current capability, and so on. So it's basically what you're doing is you're taking like a sports car, and then you're trying to drive it like a freight truck and pull a massive load, and it's just not working. Finally, there are these two classes of controls here, so-called virtual oscillator control that was invented for microgrids and is basically controlling the inverter like a self-synchronizing Van der Pol oscillator. There were some issues with this, predominantly that you cannot give it power set points, which in a large system context is not acceptable. So these things can run a system, but basically how much power is coming from which source, if you have multiple sources, is just purely determined by the network line parameters, by the physics. And this is in a large power system that you need to manage power flows is just not acceptable. So in response to this, one of the things that we developed, and this was a few years back, is the so-called dispatchable virtual oscillator control. Actually, we're not even trying to fix this problem, but to develop a control from the ground up. But as you would see in a moment, it actually reduces to that control and that one here in special cases. So to give you an idea of what these things look like, it's basically here is an equation where we form the reference voltage that the converter is imposing onto the grid. And you see this is an oscillator written in Euclidean coordinates, so basically as a two-dimensional vector. And this first term here just makes it go around at the nominal frequency. Then you're measuring the current injection into the grid, and that basically you compare it to some sort of reference, and that is basically what allows you to synchronize. So if the power injection or current injection into the grid is not what you want, you're changing your voltage, to get closer to the injection that you want to get. And this last term here is just doing some voltage amplitude regulation. What's interesting about this control, out of the many I showed you before, is that for this one we have very strong theoretical stability conditions. So for this I can give you a Lyapunov function where you can tease out a couple of things that should be obvious from a power system point of view, right? So you shouldn't overload your network. Your set points need to be consistent with the power flow equations of the system. But also some non-obvious results where you see that if you increase the line admittances, for instance, so you reinforce the network, all of a sudden you can make this unstable with a multi-machine system. That would never happen, that you upgrade a line and all of a sudden your system goes unstable. You can also tease out timescale separation arguments that in power systems are typically made but have never been made fully rigorous with theorem proof style, meaning that you can see here that the synchronization control here, you need to make it slower than the time scale of the line currents on the system. And then you have some internal controls that I didn't talk about here, and those you need to make even faster so that they're not interfering with the dynamics on these other time scales. So there's very interesting results here, but I just want to give this as a bit of a prelude to actually what I want to talk about. So let's wrap up here. The reason why this is interesting is now if you go back here, there's this parameter kappa up here that I didn't tell you about, and that determines what type of network are you looking at. Are you looking at a microgrid? Are you looking at a transmission system? And so if you configure these things as if it's a resistive microgrid, you get back this virtual oscillator control that I was talking about before that does not take power set points. If you configure it as a mostly inductive system, you get back droop control, so this thing at the top that I was showing you before. And what's interesting here is now you can play these games and you can start from this virtual oscillator control and you can place different assumptions on it and you can recover most of the controls here that are for microgrids, and these are controls that have been proposed for transmission systems. And so basically by picking parameters in the right way, you can build up these relationships and show that under certain configuration, at least, many of these controls are actually the same at least in a small signal sense. Far away from a nominal operating point, they have different responses, but near nominal voltage and given given some specific choices of parameters, they're actually not too different. So now you could say, okay, that looks like, this may give me some sort of interoperability, right? And I've shown you a stability result, so we're done, right? But we're not. There is a major problem here. And let me get back to that challenge here. If you stick to this paradigm of AC grid forming and AC grid following control as your only two choices, to operate a power system as it is today, you need a mix of both. So the problem is, you can look at an HVDC system here that's connecting to AC systems. One converter needs to stabilize the DC voltage. You can look at the wind turbine here. This is a so-called type 4 wind turbine that rectifies AC into DC, and then has another converter to basically rectify the AC that comes from the wind turbine machine. To manage any of these things, you need to stabilize the DC voltage here at some point, so you need a mix of AC grid forming and AC grid following control. Both of these controls, as we were discussing before, they only support one side of the system and basically assume that they can take whatever disturbance they're seeing there and just dump it on the other system, and that's not going to do anything, which is clearly not true, right? And another issue here is that this just we will see this in a moment, there's just a lack of interoperability between these controls. So mixing kind of these AC grid forming and AC grid following controls is very easy to construct cases where things just go haywire. And as we'll see in a moment, these may depend, for instance, just on loading. So it's fine with one loading level, you change the load flow in the system a bit and it just goes. So that's clearly bad, right? The second thing that is problematic here is that the way people study this is mostly just numerical. So let me build a large, ODE model, and then let me look at, either linearize it, look at eigenvalue sensitivities, or simulate it. But if you think of a future system that has millions of these devices here, it's clearly not going to happen. Right? I mean, we all know the numerical complexity of an ODE solver is like cubic or quartic in the number of states. So if one of these converters in some models, they have like 200 states each, then you can imagine how quickly you're going to hit a wall there. And so what we really are missing here is analytic stability conditions. And they really only exist for these existing controls if it's either 100% of these grid forming inverters. And remember, they completely neglect the source, right? There's no representation of a wind turbine or a PV panel there. It's just poof, gone, idealized away. Or if it's 100% synchronous generators. There are no results that allow you to do analytical studies of these things mixed up. And that's a key problem. Maybe.
Just to insert a little bit, there are no analytic proofs for all synchronous generators either.
Yes. Well, only.
Just to put things in context, it's not just power economics question.
That's true, but at least, with the synchronous generators, if you make some crude assumptions, like, the system being lossless and so on, I mean, then there are analytical proofs. I agree. I mean, I agree that they're very crude assumptions, but, at least then you can get somewhere. And with these things, you just can't. Okay, so let's give an example for why that's a problem, because, this may just well be me, the crazy control guy saying like, oh, I want to prove for this, and, nothing will ever go wrong in practice. But so here's an example. So this is a system where we took 3 different AC systems, one of them offshore, and interconnected it through HVDC converters. And then, you now have your choice between 3 controls. It almost like doesn't matter which of them they are, but let's just say we just pick from the standard, library of controls. And then you can just brute force, assign all the possible combinations to these converters and check for how many potential load flows in that system is that even dynamically stable, or when does it go unstable. And you see here, like the best you can do is get to like 90% of the load flow cases stable. And then if you go out here, there are various combinations where you don't even get like 10% of your cases stable. So again, I'm not advocating that you should do an analysis like this. This is just going to show you like there's a massive problem here. And in fact, the analysis that we did to create this plot image just doesn't scale beyond systems of that size. Okay, so what's really going on here is the following. As I was mentioning before, in the grid following control, you're kind of assuming the grid is just an ideal power sink. You can dump whatever you want into the grid, not cause any problems. With the grid forming control, you're actually pretending that the power converter is an ideal power source, that it can just inject whatever it wants on its AC side, and we don't really care where that power is coming from. So instead, what I will try to convince you about is that we should look at something like this, where we basically should just map power imbalances. And we should care about, energy and power imbalances on both of these terminals and kind of find the right mapping between them so that the whole system stabilizes. And basically what my claim is that allows me, to put dynamic models of the PV system, of the wind turbine and so on back into the mix, because now I'm not cutting the problem open here, but I'm, mapping between the variables that indicate basically energy or power imbalance between the terminals. And then the converter here will not burn itself up trying to stabilize the system, but basically just pass it on downstream. If there is a resource that can respond, it will respond, but if there's none, then there's none. Okay, so interestingly enough, if you try to design a control based on this, you can go back to machine dynamics. And this is not me advocating for machine emulation, but this is just trying to make an analogy to the system that we have today. So how does this work today? If you have a load step in your system, you take the power to supply this out of the kinetic energy in the machine. That reduces your frequency. Then the turbine governor system picks up on this, burns more fuel, creates more steam to basically up the power generation here. So the frequency of the machine, in essence, is really just an indicator of power imbalance or energy unbalance kind of in that system. And so we can put that back into the mix with a converter, where here I'm picking the DC voltage. I mean, I know Maria has misgivings about this, so think of this as, maybe the average of the DC voltage. But the bottom line is, in all these different power converter topologies that you maybe envision connecting to the grid, there is an internal variable in the converter that somehow corresponds to how much energy is being stored in the converter. And so what we can now do is we can tie this back to the frequency. And this is basically what I'm proposing here. So if you look at the machine, in fact, it doesn't do any of that stabilization and droop control that we were talking about. This all comes from the turbine. Right? So the machine is basically taking an electric power imbalance here, turns that into a mechanical frequency, and if that deviates, then something responds. So I'm basically just putting this back on the converter here, saying the converter just maps between AC and DC. If there's overload here that will be fed from this DC link capacitor, then I draw down the frequency. And then if there's something behind it that responds, well, then it stabilizes the converter. And to make our life a bit easier in terms of control, so you see here, this is nominal frequency. So basically I'm saying frequency of the converter should be nominal frequency plus a term that depends on the DC voltage deviation. Something that's nice here and that comes in useful when you do a theoretical analysis of this is you can also use the power imbalance between the two terminals. So if you're injecting more on the AC side here than you get from the DC side, then we're also going to draw the frequency down. What's a bit annoying though is that to do this you would need to know the losses of the inverter, which you typically don't. But you can write it like this, where you basically see that the time derivative of the DC voltage here is nothing but the difference between the power that comes from here and the power that goes out here. This you don't want to implement in practice because it has this DDT of the DC voltage here, which is a noisy signal. But you can integrate over that equation here once and just go basically to angle. And then you get like a PI control. Basically, it's DC voltage difference times a PI control gives you angle. So something like this. Okay. So now basically what I'm claiming is that this, is a nice kind of prototypical control for getting the job done. Let me just briefly show you why I'm saying this. So if you look at the response characteristic, for instance, of a photovoltaic panel, this is the maximum power point here. So for each of these, this is different irradiance levels. And here you see DC voltage. And so now if you curtail these PV generation by operating at a higher DC bus voltage than the optimum, you're somewhere here, and then a drop in DC voltage just automatically means you're increasing your power generation. And that returns to this principle that now with the control beforehand, I tied frequency deviations to DC voltage deviations, so frequency drop means DC voltage drops, and then the PV panel just responds. You can play the same game with the wind turbine, where it's here, this omega here is the wind turbine speed. You can curtail it by going at a speed that's just a bit too high, so you're not extracting the optimum amount of power from the wind. And then it has the same property that you draw the frequency, in this case the rotor speed, down you're increasing the power generation. So these are just 2 examples. So you can like take a vast, really number of emerging technologies and map them back to a picture like this, and basically now see how they would respond to these fluctuations in the system if you just expose them to it instead of just cutting it off at the converter terminal. So now let me shift gears a bit, and I will first show you how we make sense of that analytically, and then I will show you a few examples. So what we've done is basically develop kind of a library of very kind of small, cute linear models for all kinds of different components. So you see this here, for the machine swing dynamics, for a turbine governor system, for a DC source plus sensitivity. So this would, for instance, model a PV system. And then you can put all of this on a graph. So basically these things are like building blocks, and then you can assemble your big system, right? And so these nodes here that have 2 colors, they are converting between AC and DC, and then the black edges are basically DC power flows, and the red ones are AC power flows. So if we were to just use grid forming control, for instance, for this bit here, if this is, let's say, a PV installation, we would have only looked at these red dots here and at these converter nodes and ignored this bit here. Whereas if we do grid following control, we would only go up until here and just isolate this thing and analyze this thing in isolation. So like this, we can now model kind of a very complicated system just through composing these models, right? So you see here power converters coming from AC, then we have a DC network here, then flywheel energy storage, wind turbines, PV. So you can basically, by putting a few simple models together through this graph structure, you can build like very complicated systems. And then basically what my claim is that the topology of this graph here will simply reveal whether or not the system will be stable or not stable. So here are the models, and I will readily admit that they're extremely crude. So for the AC power, we just use linearized AC power flow equations. For the DC power flow, you can come up with a similar object. And these, if you know these things, I mean, this LAC and LDC here, they're Laplacian matrices, so symmetric, positive, definite, one eigenvalue at 0. And then we have synchronous machines here, mechanical power sources, so these would be turbine governor dynamics, or you can model the aerodynamics of a wind turbine as something like this. Then we have pure DC nodes. These are basically buses of the DC system. Converter nodes that convert between AC and DC, so they impose a frequency on the AC side, a DC voltage on the DC side, DC power sources, right? So you can play a lot with these things. I mean, just as an example, here's the benchmark system that we are typically using. So this is 4 IEEE 9-bus systems, and we've thrown in a few HVDC connections here and renewable systems. So you can take this thing, you can put it on this graph. I don't want you to parse this, just to get the idea across, right? Put it on a graph, like we were discussing. Then you would apply Kron reduction to take all the interior nodes out. And then you get a graph like this. And then basically what I'm after is like analyzing this is still too complicated. So what I want to get is that I can now break this apart into its DC and AC networks. And basically now my claim is that I have a stability condition that we will get to in a second, where I only need to look at those AC networks in isolation. I don't need to worry about the topology of the DC networks, and the topology of the AC networks will somehow reveal what needs to be done to make such a system stable. Okay, so we need some assumptions for this. The first one is that this overall graph, so this one here, is connected. That there is at least one node that has some flexibility to control things. So this could be curtailed photovoltaics, this could be a wind turbine, right? But this is basically just saying there's one node in this entire graph somewhere that responds to power imbalances. So it's either a machine that if frequency goes down, it's injecting more power, or it's something else that where if a DC voltage goes down, it's just injecting more power in response. There's a somewhat technical condition here that this gain here, that was the one on the power difference across the inverter, that's the same for all inverters on the same DC network. It's really just there to make the analysis work out. So you can relax this, but then the equations just explode. So let me make that assumption here. Okay, and now it gets a bit tricky. So to make sense of this, we need to partition the AC nodes. So these red dots that I had on my graph, they're representing machines. And we can partition them again into nodes that do respond in some sense to frequency deviations. So these would be curtailed wind turbines, really the rotor bit and the machine in the wind turbine, or a conventional machine, and the ones that don't. And we can do the same with the converters. So basically, we have one set where we throw in all the converters that are connected to a DC network, where there's one node in that DC network that responds to imbalances, and the ones that don't. So you see the ones that are crucial are the ones that have the O here. So those are the ones that don't respond to any deviations, right? They're basically photovoltaics at the maximum power point, wind turbine at the maximum power point. So, and now there is a slightly technical condition here where we basically break the system down into these three different groups. And I just want you to look at the picture here for now. So there is basically these three groups. And what you need for stability is that there is not too many edges going back and forth. So basically, for every node in this group N1 here, and we'll tell you in a second what this is, you need an edge that goes over here into the second group and is not connected to any other node. Make more sense of this in a second. So maybe as a clarifying remark here, the synchronization mechanisms between these devices differ a bit as to whether or not the system is predominantly based on machines, so like the system today, or is predominantly power inverters. So depending on which case you're in, you can assign, different things to these sets. But for instance, if it's a converter driven system, then you're putting all the machines over here and all the converters over here. If it's predominantly machines, then you're putting the machines that respond to frequency imbalances here, and also all the converters that have some sort of DC source behind it that responds, and everything else you put it over here. And the crucial aspect is just you need to have enough of these stabilizing connections. So basically, if you go and you apply this condition up here, what it really says is that on average, I cannot have too many nodes that do not respond to any imbalances in the system. And they need to somehow be directly connected to devices that respond to stabilize the entire system. So this is really just saying is if you take any bus in your system, draw a circle around it and check that neighborhood, it's just saying it cannot have too many of the devices that are not responding to power imbalances. So this is, even though this is quite technical, this is what it boils down to. This also recovers a lot of known results. So the conditions that I showed you before, they're immediately true if you look at a system that only contains power converters. They're immediately true for systems that only contain machines that have turbine governor systems, so the multi-machine system today. And this is where your statement comes in. I mean, this is only true under very crude assumptions. Interestingly enough, it also recovers the case that if you have no machines or converters that do not respond to frequency, so if you have converters and machines, and they all respond to frequency or DC voltage imbalances, you're also fine. And that, at least for that subset of control, that was kind of known before. And then there's also things that, even the existing results do not capture. One that was interesting, at least to me, is that if you have something like that is called a synchronous condenser, so it's basically a machine that doesn't have a turbine attached to it. It's just there to provide voltage support. And there has been a huge debate around, can we not use grid following converters, so that just do maximum power point tracking and a whole bunch of synchronous condensers to get a stable system, right? Because then we have the spinning mass, we have a notion of frequency, we have the kinetic energy storage. These results here, they hint at the fact that no, you can't do this. So in fact, what this result that I just showed you says is that if you take a system that is just machines, and it has too many synchronous condensers in it, then things are also not stable. And it's in fact relatively easy to construct examples for this. Where you take one synchronous generator with a turbine governor system, you connect two synchronous condensers to the same system, and then there are always parameters for the lines or the machine inertia where things go unstable.
Just a clarification question. What did you assume in these theorems about voltage? Is that voltage source
constant?
controlled?
You mean what?
You had that technical assumption that voltage source controlled are all identical. So all the voltages are the same and you're just playing synchronization? Or?
This is only looking at phase angle and frequency dynamics. It's assuming all magnitudes the same.
Okay, just clarification.
Yeah. And so this is where there's still a gap, right?
Yes.
So these results beforehand for the virtual oscillator control, they have everything variable. And they have line dynamics and all of these things, right? Whereas that result here has a very crude network model that's just quasi-static, and it assumes, constant voltage magnitudes and so on. So basically, for the well-known grid-forming controls, we've been able to push this much further. But this is the first time we're looking at this mapping, so we figured we start with the cuter abstraction. That's a bit easier to work with. Okay. So, in the interest of time, let me not spend too much time on the simulation result, but this is the system that we saw before, this one here. And then, we put load steps into this system here to see how it responds, basically by connecting additional load. Then we cut these DC links here to island everything, and basically just see how the system responds. You see here, in response to this load step, for instance, you're driving certain renewable generation just to the maximum power point, and then it stays there and becomes essentially unresponsive. And then here at 40 seconds, we cut these DC links to island these systems. That creates one system that really only has renewables in there, wind turbine and photovoltaics, and that also just keeps running fine. And then here at 60 seconds, we put a load step in that system, and you see now larger frequency deviations start to happen, but nonetheless, it remains stable, right? So this is just our proof of concept that in a system like the one that I've shown you before, you would normally you would need like 5 or 6 different converter controls and mix them up in just the right way to make it survive all of these things. And here you just put the same control principle everywhere, and it just works. And the study that I showed you beforehand of the decreasing stability margin for all of these different converter control configurations, we ran those things again with that control here, and it's always stable for all of them. I mean, it's just a numerical result, so it doesn't say much, but that should at least give you some confidence in these types of results here, that also in very complicated simulations that holds up. Okay, so when I presented those results for the first time, I think like a year ago, someone famous in our community went like, okay, now you've solved everything, right? Well, not so fast, right? And obviously there were many really bad assumptions underlying the model that I just showed you. It's assuming constant voltage magnitude, it's assuming all the loads are balanced, it's all just three-phase things, right? And so there are many, many directions in which this needs to be pushed forward. Let me just talk about one here today. And basically today we're analyzing the interconnection between transmission and distribution networks. Again, we're cutting the problem open here in the same way that I showed you before, and the problem is cut open with the power converters, right? As seen from the transmission, we model distribution just as an aggregate load. There's nothing actively controlled in there. Maybe it has some voltage dynamics, but really that's typically about it. For the distribution network over here, we model the transmission just as a perfect voltage source. And that, for the system today makes sense because we have all the large-scale machine-based generation is up here. Down here, we only have load, right? So not a huge deal. But now we are starting to integrate power electronics interface renewable systems here into three-phase transmission or even into single-phase. So here now red and black I'm using to denote three-phase and single-phase. And there isn't even a model that would capture the interactions that happen across this boundary here in a way that allows you to do like a pen and paper analysis. So there's very complicated power flow models, and of course you can rig up a simulation, but again the question is, that simulations don't scale, so what are the underlying principles that make a system like this work? And interestingly enough, kind of the choice of three-phase transformer winding configurations has a significant impact on how well this works. We don't want to go into too much detail here. So for this study, I'm going back to the regular droop control that I was talking about before. So we haven't really pushed that yet to these energy balancing controls I was talking about. So a very simple model here that our converters, they're imposing voltages, and this is now phase angle and magnitude, and the dynamics of the magnitude are considered in what follows. And the loads are really just constant P or Q power loads. Yeah.
Droops, so they're not physical.
Exactly. They don't map to the physics in like what I've shown before. But you have to start somewhere in modeling these systems. I mean, the plan is to eventually extend this to the same controls that we've seen before that recover the physical meaning of droop, but for now this is what it is. And when we started working on this, the first big problem that we encountered is, well, there's a lot of power flow models for multi-phase systems that you could use to model like the power flow in exchange in a system like this, but they're all too complicated for pen and paper analysis. So here's a pretty long list. I don't even want to go through this. But basically, there's nothing that's tractable from an analytical point of view. Where me as a controls person could go, it's like, oh, let me work out like an energy or a Lyapunov function. Those models are all too complicated. So then we went and we're like, okay, we've had good luck with, this graph-based approach of labeling edges as AC and DC, right, and these converter nodes. So let's pursue that direction a bit more. And basically, that's what we did. So now we have a graph-based approach here where we have different types of edges. So these could be lines, or they could be transformers, and they can be, in delta or Y configuration, by ground. I mean, so you basically see all the different transformer branches here. That's a three-phase line. And then we also have single-phase lines that could dangle off of a transformer branch here. So again, you can just put this all on a graph, and now an edge is either a transformer or a line in your system. And then you can, again, linearize the power flows on for each of these component models here and stack it up kind of into a generalized graph-based framework with an incidence matrix behind this and so on. That's not terribly important. The key point is you again want to have some notion of a Kron reduction to simplify the graph, and then that will again reveal stability conditions on the topology. I don't want to go into too much detail here, but the key point is that there are certain transformer configurations that you need to exclude. And those are basically the ones where you have buses that do not have a pathway to ground, but that get caught up in a delta winding basically, and you have no path to ground. So I'm assuming that these are excluded here, and again, I don't want to go through these technical details too much. Then you also need to ensure that you don't have like a three-phase bus here, another one here, and then you have like a single-phase network looping back on these things, right? So there are all kinds of things that can make these models very ill-posed. So we're just taking basically all of these off the table. And then you can look at stability of this, and you can recover the following result here, which basically says either you have a three-phase converter somewhere that just always puts a balanced voltage on the system, and then you have single-phase converter synchronizing to this, and then you're fine. Or you have this somewhat difficult condition here, which says that there exists at least one path between two exterior buses, so those where you have converters, that contain at least one delta Y branch, and they all traverse in the same orientation. What this means is that basically the transformer is mixing up the phases, and then all the converters can be single phase, and they will still synchronize, because at the transformer level, things are getting mixed up. And that recovers actually a result that power electronics people had observed in simulation and experiment. They called the spontaneous phase balancing of delta Y connected single phase grid forming inverters. And this, just gives you a more theoretical underpinning as to what underlying graph structures actually admit this, going beyond like a single transformer. Okay, so let me wrap up here. What I talked about, is this AC grid forming control that's envisioned as the cornerstone of future systems. And then the first result I showed was that this dispatchable virtual oscillator control actually can be used to unify various of these existing controls of the grid forming ones. Then I was talking about what we call the dual port grid forming control that supports both grid following and grid forming functions. And for this, like the interesting bit is that you can get these end-to-end small signal stability certificates that include, your wind turbines, PV, and so on, at least in a very abstract sense. A key problem that we were discussing earlier, in fact, is that I told you, you have to put the specific control there, right? But there are potentially many variations that could get the job done. So basically what we've done now is kind of change perspective a bit and see the converter as some dynamic mapping between the AC and DC port. And then the question is, how do you have to restrict this so that if you put these things together, that it works, right? So that I don't have to go to Hitachi or Siemens and say, this is exactly the control you have to use. But, this is the principle you have to use. But there's certainly, some leeway of changing things around this. Talked about unbalanced systems a bit, and then clearly one goal would be to push some of the analysis with the power sources into that framework. And then one thing that I didn't talk about is there are, of course, also constraints of the converter current limits and so on that need to be considered. And that's, a very important topic for future work.
Thank you very much. I was hoping for some questions. That's why I got out.
Sure.
So. Any questions? Yes.
Yep.
So I was wondering these results that you showed
Yeah.
about stability analysis and resulting draft theoretic guarantees.
Mm-hmm.
Are you proposing this as an analysis mechanism or a design principle to design and interconnect various networks? For example, for the purpose of maximizing stability margins, things like that.
I don't think this is particularly useful for maximizing stability margins. It's more of an existence result in the sense that, you put this control on all the converters, and, your topology of the network is somewhat sane, then it's going to work, right? So this should give you some confidence that if you start digging a bit deeper as to what this means for performance and so on, that you're not completely on the wrong track. Because if you mix the existing controls, you don't even have that confidence, right? That putting things together results in a stable system. So think of this as giving you like more of a basic sanity check. It was revealing what you kind of probably would have guessed, right? In every region of the system, you need enough responsive devices, and they need to pass on disturbances to whoever can respond, right? This is really all that it was saying. And I feel like this is all that there is to it. This doesn't say anything about performance. So the energy functions that are underlying this, you cannot really use to measure performance in a meaningful way. It's really just small signal stability. So the question as to how do you go from there and look at robustness margins and so on. I mean, this is also something we're actively looking at. Stability margins, robustness margins, performance. Because, just that it's stable could mean that you have an oscillating mode that takes I don't know how many hours to decay, right? So this is really kind of at a much more basic and fundamental level, just trying to look at what principles should be employed in the control design to make these things work.
More questions?
If I would want to model a grid forming converter from a higher level,
Mm-hmm.
how would you recommend me to do that? Could I just say, okay, I have this group function and that's followed, or does it?
I mean, that's the problem in a nutshell, right? So the converter cannot always do this, right? So this is why we include the whole DC side. And there's various reasons why the converter may not follow your droop curve. The first one is, you may be overloading the power source behind you, then the DC voltage collapses, then your AC voltage collapses that you're applying to the system, and the power flow goes haywire, and then your droop curve is no longer meaningful because it only makes sense kind of near the nominal operating point. The other thing is you may be hitting a current limit or a modulation limit, right? So at the end of the day, all of these things need to be accounted for. The problem is in the control design of the standard grid forming control, they're just not, right? They're all completely absent. So this is putting the dynamics and limits of the generation device back into the mix. It's not yet, putting modulation and current limits back into the mix. So this is something we are also actually just published a conference paper on, but it's still very preliminary work. So ultimately, the key point here is that these converters, they have very little inherent energy storage, and they can just map between their terminals. And they somehow, within their constraints, from my point of view, should do this as best as possible, to make the whole system work together. It goes back to your point about collaborative control, right? Instead of just saying, oh, the buck stops here, I'm absorbing all the disturbances myself, and then I'm burning myself up in the process, which I don't think makes sense. So now, going back to your question, I would ask, okay, in an EMT simulation, sure, you have to model all of this, right? From an analytical point of view, at the moment, the stage where we are at is, you should just carefully pick which of these constraints you want to model, because otherwise it just gets too complicated.
More questions?
Could I,
Brian? Oh, sorry.
please go ahead.
Go ahead, sorry.
Could I, for example, ask a converter to operate at just 50% and incorporate some storage and then compensate it for it?
Sure.
For these 50%, you can then do like a group control.
Cost money.
Yeah, the problem is cost at the end of the day. If you want to put storage everywhere, sure. So I think this is the main take that people will have on this is that maybe this approach that I was showing here is not really needed. You can just pair everything with a battery. But I mean, that's going to be very expensive. It's also, battery aging is very closely tied to the cycling.
Yes.
With this thing, you're cycling it every couple of minutes. They're very small cycles, but then, okay, now you may say, okay, let me also throw a supercapacitor into the mix. But you see like how the complexity just explodes, right? Whereas a wind turbine gives you a tremendous amount of kinetic energy storage for free if you're doing this. To the point even that, it's more than a synchronous generator of comparable size. It's just because the blades are so long, and with these Type 4 wind turbines, your frequency variation on the rotor is much, much bigger. And, the energy you're releasing is 1/2 inertia times frequency square, right? So there are a lot of interesting physics here that you can leverage to maybe avoid putting batteries everywhere.
Yeah, actually, we're sort of a bit talking about, I'm just curious, the part where you're talking about the assumption in the operation is that you have some of these buses where their output is dependent upon this power.
Yes.
When you're looking at these intermittent sources, so, I mean, you have some of the sort of wind turbines, if you're looking at, say, a heavy photovoltaic system. Within these stability guarantees, how are you handling the fact that maybe you just, because you are sort of requiring modeling to guarantee overhead, but with all these intermittencies and non-guarantees, how do you ensure that that overhead exists in some of these systems?
So, I mean, this is something these conditions don't account for, right? They just tell you that there should always be enough of them that have overhead. And now it's a question of how do you do this. I can tell you what we've been looking at is kind of a secondary control layer that if you want like generalizes AGC, and is sort of in real time then moving some of these set points around. So one of the things that is interesting here that I didn't really talk about, if you use these dual port type controls, I mean, there's no power set point. There was no power set point everywhere. So you may wonder like, how is dispatch even happening? And so our thinking on this is that, you as a system operator, you have kind of some knowledge about these assets in your area. I mean, you also know the weather forecast, right? So you know like how much to expect from these things in an average sense. And now you have a secondary layer that's maybe just dispatching the curtailment on these things and not not power generation specifically, right? It's just saying, this technology, let's say PV, right? We expect tomorrow around noon, that's the dominant generation resource. So you tell all of these, to back off like 10% from the maximum power point. And that's the way you would, in my mind, ensure that, there's always enough of them that are responsive.
I think maybe, go ahead, I think maybe we should finish the formal part, but it's okay. Let's record the questions.
Big picture, but very nice presentation. Thank you. So you started off with this, very compelling frequency oscillations and rotating inertia providing the storing forces and so on. So, in looking at the first bullet in here and then the other comment that you made, what if all of generation moved to distribution?
Yeah.
With the building blocks and these very clever mixes of these GFMs and so on, are they going to be enough to solve the problem when all the synchronous generators go away?
Yeah, so there's something a bit more to it. In theory, they are. But what is happening is that your frequency dynamics will evolve on faster and faster timescales. So basically, the role of inertia in the system today is really just to slow the frequency dynamics down to the point that the slow prime mover of the machine can respond, right? So now here, what is happening with this paradigm, if you say, okay, let me not even have wind, right? Because that gives significant inertia using this control. Let's just say, okay, we're just using PV, we're just distribution connecting it. All of these inverters have like 5 to 10 milliseconds worth of rated power in terms of stored in their internals, right? So that's not a lot. So what will happen is that your frequency starts fluctuating a lot faster. But then your prime mover is also many orders of magnitude faster. So where the time constant of a synchronous machine turbine is, anywhere between 4 and 10 seconds or 12 seconds, the time constant of a PV module behind these things is 1 or 2 milliseconds. So now it becomes a protection problem, right? Because the protection system in your power system is just built around the assumption that if frequency moves quickly, then something is wrong. In that system here, if you go to that hypothetical system that you outlined, frequency will move very quickly, but nothing is wrong, right? Yeah. So there are all these, system questions that follow on from this, where you wonder, like, everything today is just designed around synchronous machines. But But you know, from a theoretical point of view, I mean, from a dynamics point of view, let me put it like this. I mean, there's no obstacle in just operating that system. But basically what happens, right, I had a backup slide on this. Oh, okay, it's not showing. Anyway, sorry, let me leave it here. But it's really like take the step response of a multi-machine system, frequency over time, and just squish it. And then you get the response that that system would have.
That's interesting. So what you're saying is that the old way of thinking about it is not really the right way to think about it now. And that it's a match with other subsystems that deal with other systems.
Yeah. But again,
Yeah.
it was about we need to stop. I was about to say we need to stop recording here, but yes.
So let's thank Dominic, and then please stay. Whoever wants to talk some more, just fine. Thank you.
Thanks.